This video covers cylindrical and spherical coordinates, which give us two other ways to define a point in 3-space. Starting with cylindrical, a point xyz in 3-space can also be defined using cylindrical coordinates, which define the x and y coordinates in terms of polar while keeping the z coordinate the same. So essentially, we're turning the xy plane into the polar plane and keeping the distance off that plane, which is z, the same. The notation then is r theta z, and the conversion equations are the same. So that's x equals r cosine theta, y equals r sine theta, z equals z. These three are helpful in taking a point from the cylindrical coordinate system back to rectangular or Cartesian. Couple restrictions: we want r to be greater than or equal to 0, and theta between 0 and 2 pi. And then we have x squared plus y squared, that's equal to r squared, and tangent theta is y over x. Now, just to see how this all lays out in 3-space, so if we want to define a point in the xy plane, that's going to be theta, the angle off the positive x, that's r, and then we would go up a distance of z at a right angle, and that's going to be the point r theta z in 3-space. Right? So that's how cylindrical coordinates are going to work. XY plane is polar, and then z is the distance from that polar plane to the point. So starting with a conversion, convert the point 4, 5 pi over 3, 3 to rectangular coordinates. So we have a cylindrical point, so this is r, theta, and z. So x equals r, so 4 cosine theta, 5 pi over 3. So that's 4 times cosine pi over 3 is 1/2. And in the fourth quadrant, as this angle is, cosine's positive, so that's going to be 2. Y equals 4 times sine of 5 pi over 3. So that's 4. Sine of pi over 3 is square root of 3 over 2. In the fourth quadrant, that ratio is negative. So negative 2 square root of 3. And then z stays 3. So our point is negative 2 square root of 3, 3 in rectangular or xyz coordinates. Now going in the opposite direction, convert the point negative 5 rad 3, 5, negative 1 to cylindrical coordinates. So we have an x, a y, and a z here. So we can start by finding r, which is x squared. So negative 5 rad 3 squared plus y squared, 5 squared, equals r squared. So 25 times 3, that's 75, plus 25 equals r squared. 100 equals r squared. 10 equals r. Because remember, we want r to be greater than or equal to 0. So we don't need that plus or minus that we often get when solving. So r equals 10. Tangent theta is y over x. So 5 over negative 5 square root of 3. So that would be negative 1 over square root of 3, negative square root of 3 over 3. So the reference angle for a tangent ratio of square root of 3 over 3 is pi over 6. And we need to think about what quadrant that angle should be in. And really, you want to highlight the x and y coordinate. So if you have a negative x value with a positive y value, that would take you into the second quadrant. So this would be 5 pi over 6. Z stays z, so our coordinate, or our points, would be 10, 5 pi over 6, negative 1. And there is our point in cylindrical coordinates that's equivalent to the rectangular point, negative 5 square root of 3, 5, negative 1. Next, let's look at a few surfaces defined in cylindrical. And we're really going to highlight setting each constant equal to, or each variable equal to a constant, would be a better way to put it. So r equals a, theta equals a, z equals a. And look at what those surfaces are defined as. So if we define r equals a, well, this is going to be a cylinder of radius a, centered around the z-axis. So if we sketch this for ourselves, just so that we have a picture, it's this cylinder here, where that's the z-axis, that's the x, and the y. Right, so r equals a would be a circle in the polar plane, and then z, being any value, would extend it up into a cylinder. Right, so we have a cylinder, a circular cylinder at that, of radius a, centered around the z-axis. Right, we can even add that, a circular cylinder. Then if we have theta equals a, so if we fix theta to be equal to a constant, this is going to be a half plane. And the reason it's only a half plane is that restriction again, that r has to be greater than or equal to 0. So if we sketch this out, x, y, and z, so we would have a half plane that looks like that, where right in here, that's our angle theta. Okay, so the z-axis would be included since that's when r equals 0, and then that plane would extend out. All right, and then we have z equals a, which is also a plane, and this is one we're more familiar with. This is a plane parallel to the xy plane. And really this is the same type of surface we've been looking at since z doesn't get converted in cylindrical. So we just have a plane that's parallel to the xy plane there. All right, so just getting a sense of what each variable helps define in terms of surfaces is very helpful. And then we have two other surfaces that we're going to convert. So convert r equals 2 cosine theta from cylindrical coordinates to rectangular coordinates. So we have r equals 2 cosine theta. In order to convert this, we need to identify those conversions. So r squared, r cosine theta, r sine theta. And we don't have any of those right now. But what we can do is multiply both sides of this equation by r. And that's going to give us r squared equals 2r cosine theta. Now we can substitute the conversion equations, x squared plus y squared equals 2x. And then we can keep going a little bit here. So we can say that x squared minus 2x plus 1 plus y squared equals 1. A little completing the square. And then x minus 1 squared plus y squared equals 1. So this is going to be a cylinder. So this is a cylinder. It's just a circular cylinder that is not centered at the origin or around the z-axis. Right? So this is the cylindrical equation of a cylinder that's not around the z-axis. Okay? It's along the z-axis, just not centered around it. And then we have x squared plus y squared equals 1 from rectangular to cylindrical. So this is a more traditional circular cylinder. It's going to be centered around the z-axis. X squared plus y squared is r squared. And then taking the square root of both sides, with that fact that r has to be greater than or equal to 0, we just get r equals 1. So this surface, which is a circular cylinder, converts really nicely in cylindrical coordinates. And even the cylinder we got up here also converted pretty nicely in cylindrical coordinates. Right? So we can start to see surfaces that work nicely in the cylindrical coordinate system. And it should kind of make sense that those are cylinders. So now our other coordinate system is spherical coordinates, which define the point in terms of two angles and the distance from the origin. So this is more like an extension on the idea of polar into 3 space. So spherical, distance from the origin, we're going to call that a radius. and then 2 angles now in order to define that point in 3 space. So notationally, our point is going to be rho theta phi, where rho is the radius, so the Greek letter rho for the radius. Theta is still the angle from the positive x-axis, and phi is the angle from the positive z-axis. Right, so these are the variables that you're going to see when we're working in spherical coordinates. Now, in order to come up with the conversion equations, let's actually start with our polar diagram and build out from there. So we had theta and r, and then we went up to the point by z. So now for spherical, if we draw out that distance from the origin to that point, that's going to be rho. That's our distance from the origin. Now phi is the angle off the positive z-axis. Theta is still the same. Now in order to get our conversion equations, we know that x equals r cos theta for polar. So if we can replace r with an expression in terms of rho and phi, that would be really helpful. So with a little geometry here, remember this is a right angle. Alternate interior angles here, this is also phi. So in this right triangle, r, which is the side opposite of phi, if we use our sine ratio, sine of phi would equal to r over rho, which means r equals rho sine phi. Making that replacement in our x equation, that means x is rho sine phi cosine theta. Y is rho sine phi sine theta. Right? And again, just to highlight the rho sine phi, that was the r in our polar conversions. Now we also need to deal with z, but we can use this same right triangle. For z, we can use the cosine ratio, so cosine of phi is equal to the adjacent side z over rho, so z equals rho cosine phi. So rho cosine phi. And one thing to notice, quite a bit of trigonometric functions are required to convert in terms of spherical. A couple of restrictions here. Rho has to be greater than or equal to 0, the same way r did. Theta is still going to be between 0 and 2 pi. And then the restriction on phi is from 0 to pi. And the reason for that restriction, where we can't let it go to 2 pi and we have to stop it at pi, is theta is going to take us all the way around the xy plane. So really we just need to be able to go above the xy plane and below the xy plane from the positive z-axis to the negative z-axis. In order to go from the positive z all the way to the negative z-axis, that would only require the bounds being from 0 to pi for phi. Okay? And really the issue is if we extended it further, we would get overlap in spherical coordinates, and we're trying to avoid that overlap. So these restrictions will prevent that. And then highlighting these three, we'll take a point from spherical into rectangular, x, y, z. Then we have x squared plus y squared plus z squared. That's going to be equal to rho squared. Tangent theta, since it's the same theta, that's just y over x still. These three, so notice a little overlap. These are going to be helpful in converting from rectangular to spherical. And then this last one's just a nice bonus conversion. It's going to be more helpful for our integration than actually converting our points. But x squared plus y squared, that's rho squared sine squared phi. And that's easy enough to prove. If you take x and y and you square them, look for a Pythagorean identity, you would be left with rho squared sine squared phi. So a little extra developing for our spherical coordinates since they are new to us. But again, trig, and this is really the extension of the idea of polar now into 3 space. So convert the point 6 pi over 3, 3 pi over 4 to rectangular coordinates. So this is rho, theta, and phi, as far as the order the point is written. So x equals 6 sine phi, so sine of 3 pi over 4, cosine theta, so cosine of pi over 3. So we get 6 times the square root of 2 over 2, 3 pi over 4 being in quadrant 2, sine will be positive. And then cosine of pi over 3, that's going to be 1/2. And that's going to be 3 square root of 2 over 2. Y equals 6 sine phi, so 3 pi over 4. Sine theta, sine pi over 3. So that's 6 times square root of 2 over 2 still, times now square root of 3 over 2. So that's going to be 3 square root of 6 over 2. And then z equals 6 times cosine of phi, so cosine of 3 pi over 4. So that's going to be 6 times negative square root of 2 over 2, since cosine ratio is negative in quadrant 2. So that's negative 3 square root of 2. So our point is 3 square root of 2 over 2, 3 square root of 6 over 2, negative 3 square root of 2. And that's our point in rectangular. If we go in the other direction, so convert the point 2, negative 2 rad 3, 4 to spherical. So now we're dealing with an x, a y, and a z. So we'll start by using x squared plus y squared plus z squared to find rho squared. So 2 squared plus negative 2 square root of 3 squared plus 4 squared equals rho squared. So 4 plus 12 plus 16 equals rho squared. 32 equals rho squared. So square root of 32, 16 would be 4 square root of 2 equals rho. For theta, tangent of theta equals y over x, which is negative square root of 3. So reference angle there is pi over 3. And then again, focusing on the x and y coordinate, positive x, negative y would put us in quadrant 4. So that's going to be 5 pi over 3. And then for phi, we need to use z equals rho cos phi. So z is 4. We already found the rho value, so we have to use that in our computation. And then cosine phi. So 1 over square root of 2 equals cosine of phi. Move over to this side. So rad 2 over 2 equals cosine phi. Phi equals pi over 4. And remember, we're only looking for angles from 0 to pi. So if it's a positive ratio, it has to be in quadrant 1. So that makes our point 4 square root of 2, 5 pi over 3, pi over 4. And there's our point in spherical coordinates. So good practice converting in both directions. Now we're going to do the same thing and look at each variable set equal to a constant and see what type of surface they define. So for rho equals a, well, rho is the radius or the distance from the origin, so this is going to be a sphere of radius a. And if we draw a sketch out for ourselves in 3 space, the sphere is centered at the origin with a radius of a. That's what that's going to look like. Theta equals a. This stays the same since it's the same theta, so this is a half plane still. And now because rho has to be greater than or equal to 0, so we can draw that same sketch of a half plane here, where that is the angle theta. And then phi equals a. So if we come off the z-axis, so I'll actually sketch this one before we identify it. So if we come off a specific angle, where theta could be anything, we would take this and we would rotate it around the z-axis. And that rotation around the z-axis is going to create a cone. And we're going to actually say it's a half cone, because if you remember studying our quadratic surfaces, the cone was that hourglass type cone where there was a top and a bottom. So since here we only have the top, and this right here, that's phi, this is going to be a half cone. Now, there are two special cases that we can think about. So if phi is 0 or pi, this is going to be a half line. Or really the positive or negative z-axis would be a great way to think about it. Right? So if phi equals 0, we'd have the positive z-axis. If phi equals pi, we'd have the negative z-axis. And if phi equals pi over 2, that's going to be the xy plane. Right? So that wouldn't be a cone, that would be the whole xy plane if we go out to phi equals pi over 2. All right, so just a couple of important special cases to consider. Otherwise, phi equaling to, let's say, pi over 4 or pi over 3, that's going to give us a cone in 3 space. Let's look at a few other surfaces. So we'll start with rho equals 6 times sine phi sine theta. We're going to go from spherical to rectangular. So rho equals 6 sine phi sine theta. So same thing, we want to look for our conversion equations, which right now there aren't any. But if we can create a rho squared and a rho sine phi sine theta, we'd be in good shape. So very similar to before, except now we're using a different variable. We're going to multiply both sides by rho. Rho squared equals 6 rho sine phi sine theta. Rho squared is x squared plus y squared plus z squared equals 6y. And if we wanted to manipulate, we can do a little completing the square here. So plus y squared minus 6y plus 9 plus z squared equals 9. So x squared plus y minus 3 squared plus z squared equals 9. So this is still a sphere. Hey, just now the center is 0, 3, 0, and the radius is 3. So this is just looking at a different way to define a sphere that's not centered at the origin in spherical coordinates. Still works out nice, but not as nice as rho equals 1 or rho equals 2. And then convert z equals 4 from rectangular coordinates to spherical coordinates. So z is rho cosine phi equaling to 4. If we want to write this as a rho equals surface, we would divide both sides by cos phi, which we can express with the reciprocal trig function of secant. So 4 secant phi. And this is a plane in 3 space, so this is how we would define a plane in spherical coordinates. Not the nicest definition, because we would introduce a secant into our integration, but if this was a surface that we needed to define, we could do it in spherical coordinates as well. Now express the following surfaces in both cylindrical and spherical coordinates. All right, so we're going to start with a sphere just to take a look at what this would look like in both coordinate systems. So in cylindrical, x squared plus y squared would be r squared. Z squared stays the same, equals 16. So technically we have converted to cylindrical. If we were actually trying to integrate this, we would want to define z as plus or minus the square root of 16 minus r squared. So really we would be splitting the sphere into the upper hemisphere and the lower hemisphere in order to create bounds of integration. And then in spherical, x squared plus y squared plus z squared is rho squared. That equals 16, so rho equals 4. Again, that requirement that rho has to be greater than or equal to 0. And then we have a cone. So z equals square root of x squared plus y squared. In cylindrical, we have z equals square root of r squared, which is just z equals r. And then in spherical, z is rho cosine phi equals the square root of, well, we did define x squared plus y squared. That was rho squared sine squared phi. So this is rho cosine phi equals rho sine phi. And we don't have to worry about the plus or minus issues because of how we define rho and phi earlier on. So now to create something useful from this, we can divide both sides by rho cosine phi. So that's 1 equals tangent phi, which means phi equals pi over 4. Right, so this is the upper half of a cone, and we confirm what we established earlier, that phi equals a constant is going to create a cone. And this is how we would derive that from an equation in rectangular. So we can kind of compare and contrast cylindrical and spherical for both a sphere and a cone. Both will be surfaces that we see quite often when we get to our integration. For now, practice with our conversions, get comfortable with those since we will be using them quite often when we're setting up our triple integrals. And otherwise, I'll see you in the next video.